All right, so we're gonna we're gonna talk about Hooke's law, and it relates to force. So think of a spring, and a spring will actually create a force. It's a push or a pull. So if I compress a spring, the spring wants to bounce back, so that creates a force. If I pull on a spring, the spring will want to compress back, so that creates a force. So we can calculate the force um, from a spring when given a constant, the spring's constant, and deflection, and calculate the spring constant given the required force and deflection. Okay. So basically, what we're going to do is we're going to calculate force using Hooke's law. Now, Hooke was a scientist, and he's kind of known for a couple of things, but one of these is his law of springs. We'll circle back to this at some point in time because we'll need to revisit this when we go over energy, potential energy and kinetic energy and stuff like that. So we're going to calculate a force of a spring. Every spring has a constant. How do they calculate the constant? Well, it's kind of the same way that we calculate things in class here. We just keep measuring things, and then we'll say, oh, this spring has a constant of this. And it's just a scalar multiplier relative to distance. Okay. All right. Can I move on? All right. So we're going to do a couple of problems. It says a certain spring with a free length of 10 centimeters has a spring constant of 500 newton per meter. Okay, that's this K. How much force does a spring exert if it's extended to a length of 12 centimeters? And then question 2 is, what is the required spring constant for a spring to support 10 kilograms of mass while deflecting only 14 centimeters? So this is kind of like what your homework would be like. Okay. So I'll give you a second to write that down. And so the constant, and you'll see when we start using equations and formulas and stuff, some springs move more than others, right? There's a very stiff, rigid steel spring, doesn't move very much. That'll have a high constant. And how this relates to force is we've either got to pull really hard or not pull very hard, right? Or we got to compress, we got to push it really hard to compress it, or it's really easy to compress. So the amount of force that we apply to the spring is, I'm getting ahead of myself. I'm talking more about energy, right? We put energy into the spring, and then the spring will bounce back, so, or pull back, contract. All right, can I move on to the next slide? So we're going to talk, you don't need to write this down. We're going to talk about Hooke's law, spring constants, compression and extension, deflection and deformation. Okay. There it is. Ta-da. That is Hooke's law. The force exerted by a spring is the negative of the product of the spring constant multiplied by the deformation of the spring. And deformation or deformation is just that we're changing the original shape of that's a really fancy word, not actually that fancy, but something that you guys don't use every day. That word just means we're either pulling the spring or we're pushing the spring together. We're deforming the spring. We're changing the form and shape of the spring, sort of, right? So if I have a spring and I pull it apart, it changes the spring. If I have a spring that works the other way where I have to push it together, I'm deforming the spring. And we measure that deformation by the change in the length of the spring. You'll see when we do some examples. So on those first two problems that we wrote down, we'll do those in a minute. We're basically going to use this equation to make our calculations. Okay. So the force is equal to the negative of the spring's constant, and every spring will have their own constant, times the distance that we change the length of the spring. So it's the change in the length of the spring. We don't need to know how long the spring is. We don't need to know how short the spring is. We just need to know the change in the spring, the change in the length of the spring, because that's how we measure it. So free length is what is the free length is what is this spring like when you're not messing with it. Okay. And there's two types of springs. Okay. But the free length of a spring is the length without any external force applied to it. In other words, we could push them together, compress them a little bit, or we could pull them apart. That change in the free length will determine our value for x. Okay? If you compress the spring, it's going to be a negative x value. If you pull the spring out and stretch the spring out, it's going to be a positive x value. So make sure that you sketch out that little diagram we have there. So free length, the spring just being normal, out here living life. I'm a spring. You see me. And then we could either pull the spring, ouch, that hurts. Or you could compress the spring, ouch, that hurts. Okay? But the spring's going to bounce back one way or the other. It's going to go back to its free length. And so there's two things that we're measuring technically. We're measuring the force that we apply to the spring, right, to deform it, whether it's compressing it or pulling it apart. And guess what? Guess how much force the spring is going to exert? It's equal and opposite reaction force, right? So if I push this in with a certain amount of force, guess what that spring is going to do? Push back with the same amount of force. Now we're ignoring a couple of things. No energy transfer is 100% efficient. You'll always lose a little something to heat, friction, air friction, stuff like that. Very minimal on springs, but it happens. In most cases, that little loss is negligible. Okay. I'm really getting ahead of myself on this. Can I move to the next slide? So the deformation x is the length in meters that the spring is extended. And you could even write the word stretched. So over here when I say extended, let's sketch in there stretch. 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 Has that got a T in it or CH? I better Google it. Yeah, it is TCH, but for some reason it looks weird. Yeah, TCH. For some reason, it looked weird. And then we'll do a different color. Compress. Well, heck, we know what that is. Compress is compress. Okay. I do want to point out one other thing too. Notice, and you guys got to pick up on the subtlety of this. Okay. Notice that it's force sub S. So the formula, we're calculating a spring force. That's what that S stands for. We're calculating spring forces. Okay. Cars, depending on the cars, they probably, some of them still use springs on the wheels. And the springs just kind of absorb the shock of hitting a pothole or going over a bump or something like that. A lot of off-road vehicles, ATVs and stuff like that, use heavy-duty springs and stuff. Trucks have springs on them. They have shocks too, which kind of do the same thing, but they have a combo of both, which is good. Okay. Can I move on to the next slide? All right. So write this down. The deformation X of the spring depends on how much force is exerted to stretch it or compress it. Whoops. That's an important thing to kind of write down. I typed in stretch in Google to double check the spelling to make sure I spelled it right. And it said stretch means warming up for a physical activity. So a perfect example of force and springs, I don't know if you guys remember, but oh, we never did that with you guys, so never mind. All right, can I move on to the next thing? So Hooke's law describes an ideal spring. It's a good approximation for real springs. Yeah. Did you fill out all the stuff? What? Did you fill out the thing online? What? The bathroom pass thing? Oh, it's yeah, it's in Canvas. Fill it out real quick. Okay, but you still got to take that too. So remember, force is measured in newtons. The spring constant is newtons per meter. And the deformation, which is a fancy word that means how much did we stretch or compress the spring, X. Now they say ideal because what happens with these springs, a spring, if you pull a spring and you hold it for a really long time, it doesn't pull back as quickly. Okay? And you might actually stretch the spring. So they're saying an ideal spring, what they mean by that is that it automatically goes back to the way that it was perfectly. Okay, springs over time, if you stretch them because they're metal, you can literally stretch them out. So then the force isn't the same. Same thing if you compress them. If you take a big heavy-duty spring and you compress it and you just hold it for a very, very, very long time, the molecules will kind of realign themselves, and then when you let go, the spring isn't as long. So we're saying, real quick snap, right? An ideal spring. So as you guys are experiencing through your labs, all these equations are ideal situations where everything goes perfect and smooth. Oops. And like everything that we're doing in this class, everything has to be converted to meters. So if you remember that first problem, it was in centimeters. So we got to convert that to meters before we could do that. Okay, can I move on? Oops, wrong thing. So this is how they figure out the constant K. So go ahead and write this down. You can measure the amount of force that you apply to a spring and how much it moves. So if I push against a force of 10 newtons and it moves, I don't know, 5 centimeters, I could do some math and that'll give me the constant K. And like everything that we do, they do that with a bunch of springs and take an average. Okay. So the spring constant tells you how much force is needed to deform the spring a certain distance. And that, like I said before, that could change over time, but most of the time, you know, whatever you use a spring for, the precision level is, you know, if you're off by a millimeter when you go to do your calculations, the practical applications of springs and how we use them in the real world, that 1 millimeter doesn't really matter that much. So if you notice, this formula is just the first formula algebraically rearranged, right? If you took that first formula and used algebra and just solved for K, you would get negative F over X. That's also why it's newtons per meter. Okay. All right. Can I move on? So the spring constant tells you how stiff the spring is. The greater the constant, right, the stiffer the spring. And we can actually, you know, Mr. Adams is also the robotics coach, so we use springs a lot on the robots. So sometimes we want a really stiff spring. For example, our robot had a climbing mechanism, so it could do like a pull-up. Our robot weighed like 120 pounds. So our robot literally lifted itself up, which was like 120 pounds. Now, how we did that was interesting, but what we basically needed a spring to take that mechanism and make it go up. So what we did is we took the climber and we compressed the spring and compressed the climber all the way down, and then we had like a winch attached to it. So when we released the winch, it would go up. The spring was forcing it back up. And you know, we could have a stiffer spring or a weaker spring. So we found one that worked best for the robot. Now, a low constant means the opposite, that you have a weaker spring. Okay. And that just means it requires less force. Let me move my face out of the way so you guys can write that stuff down. Now it says, which of these springs has the higher constant? I just want to remind you guys that vectors, the length of the arrow that represents the vector tells you the magnitude. They've moved the same distance, but one has a longer vector for force. So the top one is the stiffer spring because my force vector is longer. You can examine the graph of the spring versus deformation. Notice that it's linear. So when we think of force equals negative kx, isn't that kind of like y equals negative mx? Yeah. So the slope of the force versus the deformation, or the change in the length of the spring, will be a straight line for springs. So it's a linear relationship. That's how they knew that equation would work. They just started pushing springs or pulling them and graphing how much force. And so to deform a spring more, you would have to apply more force or less force. But the relationship is linear. We're almost done with our notes, guys. And so here's a little bit of math. It's kind of hard. I got to move my thing. It'll show in a second. But basically, they're saying, think of the slope. You calculate the slope. That's the constant, the rise over run. Okay. Your constant is the rise over run. Let me move that out of the way. So the only thing that I would add is that this is actually um, your spring constant. Okay. All right. So I think we're going to stop there for now. Well, wait. Let me see. Does everybody have this written down or no? I see some people kind of leaning this way. Let's see. That bottom's kind of hard to see, isn't it? That's a great big thing, but I don't think they anticipated. I wonder though if I made this smaller and moved it up, like does that help if I do this? If I make it smaller, or is it harder to see because it's smaller now? I don't know if that helps or not. Because that's a humongous screen. All right. Let's see the next slide here. Oh. You don't have to write this down. The magnitude of the slope is the force that's exerted. So we're just going to skip past that. We're going to skip past that. Yep. So we're done with that.